you will remember from Friday, we did a little clicker quiz thing, right? And we corrected it, I think, right? And I gave you the answer, right? You sort of left off there. Okay, good. So we're going to spend a couple more days sort of reviewing some of that graph theory. More with a focus on DC graphs, because you spent some time in grade 10 on displacement time graphs, and you certainly spent lots of time in grade 11 on displacement time graphs and velocity time graphs, but I'm going to sort of review some of that BT graph stuff over the next few days. So today we're going to look at just basically what we did for probably about 4 to 5 days in grade 11, condensed, crunched down into one day. Yeah. And I'm going to use the textbook for that. I don't use the textbook a whole lot. How many people got a notification on their device or computer? Was it Sunday?
Yeah.
You know what I said? Last night. Last night. Okay. So hopefully you. Oh yeah. Okay, we'll get you in there. Okay. So hopefully you all have your text. What I did was from your textbook, I just sort of cut out the important graphs. I'm going to sort of go through the text, explain stuff, write some stuff on these graphs. I would suggest you sort of take your notes right on that page. Rather than you redrawing the graph and everything, this is a better way to do that. So I'm just going to make it up as I go. Okay? If need be, if you need a refresher on displacement time graphs, then that starts really on page 14 in the book. 3 steps to graphical analysis. That's sort of some very basic stuff. Page 15, analysis of straight line DT graphs. I started that with my grade 11 this morning. Talks about reading graph, finding slope. That I'm hoping is all old news for you guys, right? 1.6 on page 19, analysis of curved line DT graphs. Again, you should sort of know that already. I'm going to start in chapter 2. Chapter 2 is velocity time graphs. So 2.1, page 38. 2.1, page 38. If you need to share books today, that's fine. We're going to be using them over the next week or so, so bring them every day this week. All right. In the last chapter, we found velocities from displacement time graphs by taking slopes at different times. In this chapter, we will use these values to create velocity time graphs and analyze them using the 3 primary analysis methods for graphs in the last chapter. So constant velocity graphs. A motorcyclist traveling along a straight level road past markers at 40, 100, and 160 meters at the times you can read on the graph in figure 2.1a. And you have that right here, right? So this is a position time graph. So it's where they are at certain points. The DT graph is a straight line. What does that mean? It's a straight line, DT graph. They aren't moving? The DT graph, straight line like that. Not flat, straight. Constant speed, right? Constant speed, good. Slopes at the 3 points in the graph are recorded in the table in figure 2.1b and plotted on the DT graph in 2.1c. So what they did was, they found the slope at those 3 points. Now how do you find the slope of a single point on a straight line graph? Can you find the slope of a single point, right? Rise over run is correct, but can you find the slope with a single point? You gotta have 2, right? Now the idea is that because it's a straight line, the point right there, right? The slope there is the same as the average between those 2 points. So what they've really done is they've taken those 2 points, found the slope, rise over run, that I'm hoping is all review for all of you, right? Should be, right? So here they found the slope to be 20. Here they found the slope to be 20. Here they found the slope to be 20. Not surprising, but the slope is the same because it's a straight line graph. The slope is the same. The slope is constant, right? And then they simply took these x values of 2 and 5 and 8 and wrote down a velocity of 20, 20, 20. Constant velocity, right? I'm going to write here constant slope. And what does that mean? Constant velocity. And we spent a considerable bit more time in grade 11 developing that idea. I'm just sort of, think of today as like restoring deleted files from your recycle box on your desktop. Okay, and then we took those constant velocities and we wrote them in a table here. And then what did we do right here? We graphed them, right? And at 2 seconds, 20, 20, 20. Constant velocity. I thought this shape was constant velocity. Different graphs, exactly. Position time graph, right? Velocity time graph. Different graphs showing the same thing. I'm kind of looking around the room for the head nodding. Kind of gives me an indication of how much it's making sense. If it's not making sense, then give me this one here, just very subtly. Okay. All right. All constant velocity, right? Okay. So down below it says reading the graphs in Figure 2.2, which is. Do you have 2.2 on your page?
Yeah.
Do you really?
Hold on.
Oh, on the next page? No, you have 2.3. 2.8. But really, if you look at 2.2 in the bottom left-hand corner, it's really just the same graph as this one, just minus the motorbike, right? Same graph. Okay. In Figure 2.2, the units of the y-axis are meters per second, which indicates velocity. Since you're reading a given velocity at a given time, reading this graph allows you to find instantaneous velocities. Remember that two-column thing that I went through? How do you find velocity from a velocity time graph? You just read it. Finding the slope of the graph. To find the slope of the graph in Figure 2.2, note that the horizontal graph has no riders. Thus, for any value of delta t, the value of delta v will be 0, and the value of the slope here is 0. And you can see the calculations there, right? Slope equals 0, and you'll note that those units are meters per second divided by seconds, or meters per second squared. And what does this mean? Oh, you know what? One of these summers I'm going to practice my handwriting. The acceleration is equal to 0, which means it's traveling at a constant speed. I'm just coming back to that over and over again, right? Top of page 39. The slope calculation produces a value of 0 with units of meters per second squared. This quantity is the change in velocity over a given time period. We can see that if an object has constant velocity, its acceleration must be 0. The process of change of velocity is called acceleration. The units for acceleration are distance over time squared. By finding the slope of the VT graph, we have produced the following equation: A equals delta V over delta T, which you already know, right? Okay. Hey, Mr. Love. What can I do for you? Interestingly enough, and you may never have seen this before, I don't think I showed you this, maybe you figured it out on your own, but if you think about slope, as being rise over run, what's the rise here? The y-axis is velocity, so what is the rise? It's the change in the velocity, right? The delta y is delta v, delta velocity, and the run is how much the x-axis changes, which is the t. And what is the slope? Well, it's acceleration. It's really a graphical derivation of A equals delta v over delta. It's really what it is.
She'd like me to decipher that.
She knows the code.
She told me to come and see you.
Oh, she's just complaining? Okay. Blah, 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 blah. See where it says find the area in the graph? See that there in the text? Okay. What does the area under a VT graph represent? Do you remember? Displacement. Consider positive to be north. In Figure 2.3a, the area in the graph forms a rectangle. Is this probably on the next page? On yours, it's in the middle there. I'm guessing on mine, it's right there, yay. Consider positive to be north. In Figure 2.3a, the area under the graph forms a rectangle. So its area is obtained by the relationship length times width, which you learned in about grade 4 or 5. In our case, the length is time, and the width is velocity. We can represent the area of the VT graph as V versus T, and by doing a unit analysis, we see that, and I'm going to write this here, right? Rectangle, length times width, if this is your length, and this is your width, or vice versa, it doesn't really matter, right? So the area is length times width, and the length is the time, and the width is the velocity, right? I guess maybe would you be mad at me if I write width? Would you be mad at me if I wrote width times length? Is that the same as length times width? So after all that, you're taking the laptop?
Yeah.
Oh, okay. Really? Velocity multiplied by time. And what's velocity multiplied by time? Displacement. That's the area, right? And then it talks there in the textbook about unit analysis. This times this unit is meters per second, right? Up here. This unit is seconds, so meters per second times seconds. What happens when you do that unit canceling? The seconds cancel, and you're left with the unit for the area is meters, and what do you measure in meters? Displacement. I'm just sort of showing you different ways that it all fits together. Again, it should more or less be reviewed. So this indicates that the area represents the distance. In other words, the area represents the displacement of the object during the chosen time interval. Okay, so for example, this particular one right here, right? The time is 5 seconds. The velocity is 20. The area is going to be 5 times 20, or 100 meters. Can you guys read that? 5 times 20, or 100 meters. The area under a VT graph is the displacement. The displacement is in the positive direction because the area is positive. If the velocity is negative, as in figure 2.3b, the displacement is also negative. This one here, can you see that it's below 0? Okay. So the displacement here is the area. Looks like it's going to be 5 times minus 15 minus 75 meters. It's traveling at minus 15 for 5 seconds. Right? Am I making sense? Help me out. Right? I'm making sense. Speaking English? Good. Okay. At the bottom, 3 graph analysis techniques for VT graphs. You can see the flow chart in the textbook. I purposely cut it off. Why did I do that? It's not because I'm a jerk. Well, I think that if you write it down, you got a better chance, right? Of remembering. I'll write it down too with you just to prove that I'm not being a jerk. Okay, so if you've got a VT graph, what can you read off a VT graph? Well, it's measured in, the units are meters per second. You might want to just write units above there. They don't have it in the book, but I think that helps. The units are meters per second, and so what is it that you are reading? Instantaneous velocities, right? What is the slope of a VT graph? Meters per second squared. And what do we measure in meters per second squared? Acceleration. And what unit do you get when you find area? Meters. And what do you measure in meters? Displacement. Do you remember that week with the booklet that we went through all this stuff in grade 11? Yeah? No? Now, all of this is true when the graph is straight. Flip the page over. Both in the book. We're now on page 40 in the book. And the handout. Now we're going to talk about Graphs with a changing velocity. Is everybody with me? Graphs with changing velocity. Here we have a position time graph. What word would you say would you use to describe that position time graph? How would you describe that? Like the shape. Curved. I would say curved. Not straight. Okay. On a performance test, the Honda Civic produced the DT graph in figure 2.5a. As you saw in chapter 1, a curved DT graph means the velocity is changing. Find the slope of this graph at 4 different points, gives the velocities as shown in 2.5b. Applying these points gives the VT graph in 2.5c. Okay, I'll translate that for you. So, if you look closely, both in the book and on your sheet, you will see tangent lines. And there's even one right at the bottom. You just don't see it very well. There are 4 tangent lines because when you need to find instantaneous slope, you draw a tangent line, you pick 2 points on that tangent line, and you calculate rise over run. And when they did that, here at 0, they said it was flat. They got a slope of, these are slopes, right? They got a slope here of 0. They got a slope here of 6. Here they got the slope of 12, slope of 18. Is the slope increasing? Certainly is. Which means the speed is speeding up, right? Speeding up. So these are my velocities, and then they took these values here and they simply graphed them. Okay? It's exactly the same process as we did right here, but here the slopes were all the same. Slopes were all the same, and the graph was flat. The velocity time graph was flat. Here, what's the velocity time graph like? Not flat, but still straight, right? Remember, there's a difference between straight and flat. And so the values here at 0, it's 0. At 1.5, there's a dot right there. At 1.5, it's 6. At 3, it's 12. And at 4.5, it's 18. I have no idea why they picked those points. This is increasing velocity, right? Everybody with me? Down below the graphs in the textbook. Figure 2.5c shows a steadily increasing velocity. The velocity increases, the object is accelerating. To find the acceleration, we find the slope of the VT graph. When you find the slope of this, pick 2 points and find them. They used 18 minus 6. 18 minus 6. These are the points that they're using here. These ones here. 18 minus 6 all over 4.5 minus 5, and you get 12 over 0.5? Well, it's not. It's 1.5, sorry. Over 3. Or 4 meters per second squared. The slope of this velocity time graph is a constant 4. This object is accelerating at 4 meters per second squared, which means that every second the speed is increasing by 4 meters per second. Everyone's with me? Kind of checking in here every once in a while. What was the acceleration in the last situation? It was 0. Why? Because it was flat. No acceleration. Here it's 4. The value for the acceleration is a positive number. The sign indicates that the acceleration is in the same direction as the velocity, which means that the car is speeding up. Its acceleration is 4 meters per second. Do you want to take the whole cart there, Mrs. Gunn? Yeah. Whatever you want. If you think it's easier to take 9, then go ahead. That's fine too.
Is it plugged in?
It is, yeah.
I figured out why I lost.
In the previous graph, the area was easy to find because it was a rectangle. Now what's the area? Go help her out, Ryan.
You're causing a ruckus. Okay. Hopefully.
What's the area here going to be? Not a rectangle. It's going to be a triangle. How do you find the area of a triangle? Base times height divided by 2, or some people prefer half the base times the height, right? That's what they're talking about there at the bottom. Find the area in the graph. The area under the graph in figure 2.6 is a triangle. The area of a triangle is half the base times the height. By substituting values and units in the graph into the equation, we obtain 1/2 the velocity multiplied by the time, and the area there of that one that I don't think I have shown, but I've sort of done it right here. The base is 3.5, the height is 14, 24.5 meters. .5 times 14 divided by 2 because it's a triangle. Is that what it is? 24.5 meters. Rounded off to the correct number of significant digits, the answer is 24. Should we have the significant figures rant right now? This is the usual spot. So round that to 24 sig figs, right, boys and girls? Okay, example 1, working with negative motion. I'm almost done, you guys. Getting close. Now we gotta wait. Repeating the test drive in figure 2.5 in a westward direction, produce the VT graph of 2.7, calculate the acceleration, and reconstruct the VT graph. Oh, this is more than we've done already. Okay, does everyone know where we are? Okay, we're on page 41, and we're looking at this graph right here. This velocity time graph right here. So they want you to calculate the acceleration and reconstruct the DT graph. They didn't give you the DT graph, you have to figure it out. Finding acceleration first. In the standard reference frame, westward is negative, hence the velocities are negative, but that does not change the process to find slope. Figure 2.7, the slope of the VT graph gives an acceleration of -4 meters per second squared. So they found this slope right here, looking at this graph right here. Can you see what the rise right here is -8? Do you see that? Right there, right? And so the slope, or the acceleration, is going to be -8, and the time, the rise is from 1 to 3, is 2 seconds. The acceleration is -4 meters per second squared. That's relatively easy, finding slope. The hard part is the next step. How do we reconstruct the DT graph? Part B. To find displacement, we once again find the area. This time the area is under the time axis, stretches down to the velocity line. Excuse me. Okay, so we are reconstructing the DT graph from velocity time. We need multiple points. Okay, so to get multiple points, we're going to find multiple areas. This is a bit small. I'm going to make this a bit bigger. So I'm looking at this graph right here. Do you see how it's labeled A, B, and C? Okay, now really, A is this triangle here, B is this, I guess that's a trapezoid, and C is this trapezoid here, right? So I'm going to find multiple areas. The first area I'm going to find is area A, and it's down here for you. Area A is 1/2 the base times the height. Base is from 0 to 1.5. Do you see that? 1.5. The height goes to -6. Just take my word for that. So the area of area A is -4.5. That's this guy right here. Okay? Area A plus B. So that one plus that one there. Well, A plus B is another triangle, right? 1/2 the base goes to 3, the height goes down here all the way to -12. 1/2 of 3 times -12 is -18. That's the area of A plus B. That's how far it goes in those first 3 seconds. And then they took A plus B plus C is this big triangle here, which I will mark in black. Right? Base is all the way to here to 4.5. Down to -18. 1/2 of 4.5 times -18, -40.5. So now I've got 3 displacements. I have to reconstruct a DT graph. So what am I going to do? I'm going to graph. They just wrote those numbers down again right here. with the corresponding times, I now have time and position. How do I get my displacement time graph? I simply graph, right? These are areas, right? These are areas which are equal to displacements, which are written down in a table and then graphed, and this is the corresponding GT graph. Is it surprising that it's curved? It shouldn't be. Dane, why is it not surprising that it's curved? What's the velocity doing here? Is the velocity changing? It is, and changing velocity is shown in the DT graph with a curved line. How come it's down below, Alex? What's negative? Why is the position negative? Because the velocity is negative, right? The velocities are negative, therefore this is it. Is the slope getting steeper? Yes, and remember, the velocity time graph is a graph of the slopes. Here, the value of the graph is getting more and more negative. Here, it's because the slope, right? They're corresponding. Is it all coming back to you? Maybe in bits and pieces? Maybe. Okay, real close, my friends. It's a long period, isn't it? Let's look at example number 2. When velocity and acceleration have different signs. This one here, Chandler, position was positive, velocity was positive, right? Here we've got negative velocity, negative position. What if negative acceleration? What if they're opposite? That's what's happening right here in this one here. For the slowing down portion of the roller coaster ride, I don't know what roller coaster ride they're talking about, find the acceleration. Okay, so we have a position time graph right here. For this case, we'll use the DT graph in Figure 210. Figure 210 shows the process of creating the VT graph from slopes on the DT graph. To find the acceleration, take the slope of the VT graph. So what did they do? Here is a position time graph. Did I move that? Here is the position time graph. They drew tangents, only 2 of them. They found the slopes. Here they said it was 30 over 1 at 0. So the velocity at 0 is 30 meters per second. At 3, which is right here, they found the slope. It went up 24 over 2. 24 over 2 is 12. And here's one more tangent line. I lied. There they said it's flat. So the velocity is going from 30 to 12 to 0. And then they took that data, they put it in a table, and then what did they do? They graphed it.
That's the worst part of the roller coaster. Then you have to get off.
Yeah. You can always ride again.
You have to wait more.
Yeah, wait in line again, I know. The velocity is going down. The velocity is, I like to say, approaching 0, which means it's slowing down. How do you see slowing down on a position time graph? The slope does what? Gets flatter. The slope gets flatter, it's slowing down. Here is going down to 0. Okay? And we're supposed to find the acceleration. How do you find the acceleration? Find the slope of the VT graph. The slope of the VT graph here. Pick any 2 data points. I'm going to go 0 minus 30. And I'm going to go 5 minus 0. Minus 30 over 5, or minus 6 meters per second squared. The roller coaster is slowing down at minus 6 meters per second squared. When the position is positive, when the velocity is positive, but the acceleration is negative, that means that it's slowing down. Okay, and that's what they're talking about there on the bottom of page 42. I didn't do that flow chart. I think you guys know that already, right? Like if the velocity is positive and the acceleration is negative, slowing down, right? Or vice versa. Anytime those signs are opposite, slowing down. When they're together, they're speeding up. Okay, last one, and then I'm going to give you some time to work. Time are we done here? 2 14. I apologize for the length of this lecture.
Wonderful.
Oh, you're just saying that to make me feel better. Thanks for trying. Do you see on your paper, if you look closely in the textbook, do you see in sort of light green, it kind of looks like this? Do you see that? Okay. Someone in the visual arts department went and did that. It has nothing to do with the graph. They're, in my mind, putting bad thoughts in students' minds. I wish they wouldn't do that. But they're trying to make it more visually appealing, and it's just confusing people. Yeah, and here's the other thing, right? We're riding this bike, we're going up and then down. Okay, and then you'll see another problem here coming up right away. So a lot of traveling and ending up nowhere, kind of like this little lecture. Thank you, Wyatt, yes. Figure 212 is a VT graph of a cyclist's motion. The cyclist traveling at 20 meters per second arrives at the bottom of the hill, climbs up the hill to a stop, and then coasts back down again. Find the total displacement as well as the acceleration for each section. Do you have written in someone's handwriting where it says total displacement, do you have the word vertical written in there?
Yeah.
You do, and it should be there. They want to know the total vertical displacement. You start at ground level, you go up, and you come back down. What's your vertical displacement? 0. You're at the same altitude as you were before. What's your horizontal displacement? Well, whatever it is from here to there, right? When it just says total displacement, which one of those two things is it saying? We don't know. Which is why I have kids write in vertical, because that's what they're really asking. That's what the answer is.
So if they arrive at 20 meters per second, does that mean they're already going up a hill when you start counting?
Yes. Now, from the graph, how do you know they're traveling at 20 meters per second? Well, that's this point right here, isn't it? Right? What's this point down here? It's nothing. It's a picture of the hill superimposed over top of a graph. It's nothing. It is not. This red is not a graph. It's the hill. Get rid of it. It shouldn't be there. It's confusing. It's almost better if I don't mention it, but some people get confused by it. It's nothing. Okay, so we're traveling at 20 meters per second. And as we go up the hill, as you know, what happens to bikes as they climb up hills? Slow down. At what time has this person reached the top of the hill? At 4 seconds. I think that's what that was. Right? They're at the top of the hill there. How can you tell? Because the velocity is 0. On the other side of the hill, what happens to their velocity? Well, it becomes negative. Why? They're going downhill. Now, here's another problem. If you're going to the right, that's positive. If you're going to the left, that's negative. And I got no problem with up being positive and down being negative. But up a hill is positive? And down a hill is negative? And isn't the direction change as you go up the hill? You're sort of pointing like the direction's changing all the time, right? It should not be positive and negative. The vertical component is up is positive and down is negative, right? But this bike's also moving forward. It would have been much better if it had just been something thrown straight up and straight down. Would have been a much better example.
And like, you don't actually have to stop. Okay, like that.
No, you wouldn't actually, right? And there's another good point. The velocity, the overall velocity, is not 0 at the top of the hill. What is 0 at the top of the hill? The vertical component. We haven't talked about components yet, right? Yeah. Really, really bad example. This is a wonderful example, a really good example of a bad example. Should not be in textbooks. If you're writing textbooks, don't put these things in it.
This would be better in the orbital mechanics.
Well, no, it would be the projectile motion to the vectors. Okay, so anyways, back to the actual question. Vertical. Find the total displacement as well as acceleration. So under displacement there, calculate sections A and B, making sure to keep track of signs. Add the two parts to find the total displacement. Consider up the hill to be positive and down to be negative. So what is the area in here? I'll label this A and this one B. Displacement A, 1/2 the base times the height. The base is from 0 to 4. And the height is from 20 to 0, right? Half of 4 is 2 times 20 is 40 meters. That's the area of A. The displacement of area B. 1/2 the base times the height. The area is from 4 to 8-ish. They don't even show an 8 on there. And the height is down to -20. Oh, hang on here. Did I make a mistake? I made a mistake. What mistake did I make? And I didn't do it on purpose. But I caught it. The base is not 8. The base is from 4 to 8. Do you think that students might make that mistake?
Yeah.
Yeah. So it's from 4 to 8. That's a total distance of 4. Height was -20. Again, 40, but this time it's negative. Total displacement, 40 minus 40 or 0. As I said earlier, you end up at exactly the same altitude as before. 0. You don't have a lot much more room there, but what is the overall acceleration of this trip? Well, the acceleration is, give me about like 5 more minutes, you guys, okay? I know it's, I recognize the length of this sitting around and listening to me. I'm going to try real hard not to make this happen too many times. What is the acceleration? It is the slope of the VT graph. Find the slope of this line. Does the slope of this line change ever? It does not, which means the acceleration is constant. Any 2 points, I don't care. The slope here, let's just go this point and this point. So that's going to be 0 minus 20 all over 4 minus 0 minus 20 over 4, or minus 5 meters per second squared. Minus 5 meters per second squared. That's on the going up the hill portion. What about the going down the hill portion? Same thing. How can that be? How can the acceleration be minus, but on the way up you're slowing down, but on the way down you're speeding up? Because the velocities are different, right? On the way up, the velocity is positive, and the acceleration is negative, which means slowing down. But on the way down, the velocity is negative and the acceleration is negative. They're both the same, both negative, so it means speeding up. The acceleration is the same, which tells us that the slope up the hill is the same as the slope down the hill. If I take anything, a penny, and I throw it up in the air, at what rate does it slow down on the way up? Minus 9.8. And on what rate does it speed up on the way down? Minus 9.8, both the same. The acceleration is constant. Same thing here. Okay, I'm going to wrap up because I have overstayed my welcome. Go right to the chart. So, this is the same information as those 2 columns, right? It's exactly the same, just in sort of a flow chart kind of format. So write this in, and then we'll be done here right away. Information obtained from a VT graph. So, when you've got a VT graph, what do you read on a VT graph? Or I like to call it V-inst, right? Instantaneous velocity, V-inst. If you've got a VT graph and you're finding slope, well then you're finding acceleration. And if it's 2 points that you're using, well then you're finding average acceleration. And if you're using only 1 point, how can you find slope at 1 point? Tangent line. So if you need a tangent line, well then you're talking about A-inst. A-inst. Right? Instantaneous acceleration. If you have a VT graph and you're asked to find area, or if you do find area, then what are you getting? displacement. And if you take that area, that displacement, and you divide it by the time, then what do you get? You get average velocity, which is really V bar, right? Average acceleration is A bar. Again, I point out, if you're with me in grade 11, we went through all that stuff. It just took us about 5 days. Have I successfully blown your mind? Not really my intention, but it does happen. Okay? All right. You need some time to work with this and figure this out. That was sort of the refresher. Okay? Don't get too excited. At the bottom of the page there, do I have it on mine? I do not. Yeah, page 46, number 1 to 4 in the book. Page 69, numbers 14, 15, 19, 20, and 21. Now, before I get too much farther, because the graphs in the book, I don't want to write in the book, so what I did was I just took the exact graph that you have in your textbook that you all have copies on. When I'm saying that's the copyright reasons, I'm not allowed to copy photocopy textbooks, because we already own the textbooks, I'm allowed to do it. I'm not breaking any laws. I wouldn't do that, Ryan. So here's the graph, just work on here. Okay? I'll give you this right one.